Now let us look into the algebraic side of these projective algebraic sets. So in the affine setting, we used ideals in the ring of polynomials to algebraicize these sets. In this setting, we have to be careful about this homogeneity business, and that is why we need to be careful about the structure of the polynomial ring as a graded ring. What does it mean that the polynomial ring in n+1 variables is a graded ring? A graded ring is a ring that, as an abelian group, is the direct sum of some parts here. So this is a direct sum of abelian groups with respect to the additive structure of the ring. And the product should behave in such a way that the product of an element of degree d, so these RDs are called the components of degree d, their elements are called homogeneous of degree d. So an element that is homogeneous of degree d multiplied by an element that's homogeneous of degree e should be homogeneous of degree d plus e. And in our case, RD is just the, so RD is the set of polynomials in this ring such that the degree of f is equal to d. They are, so to speak, of total degree d. And then all of this holds because of how the degree behaves when you multiply. Notice also that maybe this is more relevant for the general setting than for this specific case where this is clear, but the direct sum means that any element can be written as a sum of finitely many homogeneous elements. So in the direct sum, we require that we can decompose any f as the sum of fd, where fd is in Rd, and almost all of these fd, meaning all except finitely many, are 0. So the polynomial ring is in fact more than a graded ring. Since it's more than a ring, it's a K-algebra, and it is also then a graded K-algebra. And so the action of K doesn't change the degree. That is what graded K-algebra means. And the decomposition of an element of R as a sum of homogeneous elements of degree d, where the sum goes over the natural numbers with all but finitely many equal to 0. This is called the homogeneous decomposition of f. So now that we know that our ring of polynomials is graded, we will look at special kinds of ideals that respect this grading. And first, we note the following property, that if we have a graded ring R and any ideal J in R, then the following two properties are equivalent. One is that J is generated by homogeneous elements. So this means that J is generated by some f such that each f belongs to some Rd. And the second statement is the statement that if you have f with a homogeneous decomposition like this, and if you know that f is in your ideal, then all the homogeneous components themselves have to be in the ideal. These homogeneous components, because of the direct sum decomposition, are unique, so this statement makes sense. And I leave it to you as an exercise to show that these two definitions, or these two properties, are equivalent, and they serve as the definition of a graded ideal, also known as a homogeneous ideal. So it's an ideal satisfying any and hence both of these equivalent conditions. So it is an exercise to check that if you have two graded ideals, then their intersection is a graded ideal, their product is a graded ideal, and their sum is a graded ideal. And if you have a graded ideal and you take its radical, then the radical is again a graded ideal. So, for example, in K T1, T2, the ideal generated by, say, T1 and T2 squared is graded because it's generated by homogeneous polynomials, but the ideal, say, J prime generated by T1 minus T2 squared is not graded because it doesn't contain T1 and minus T2 squared, which are the homogeneous components of this polynomial. So now we can define the zero loci of graded ideals. So go back to the definition of zero loci in projective space of homogeneous polynomials if you have forgotten what that is. And so now if we have an ideal, a graded ideal, a homogeneous ideal in the polynomial ring in indeterminates T0 to Tn, its projective zero locus V of j, Vp of j if we need to emphasize projectivity, it's the set of all x in projective space where all homogeneous elements in J vanish. So this is important because in general we cannot require any arbitrary element in J that is not homogeneous to vanish, that is not well defined. As in the affine case, it is no restriction to only consider zero loci of ideals rather than arbitrary sets. Because if you have a set of homogeneous polynomials S, then you look at the ideal generated by these homogeneous polynomials, and this gives you a graded ideal. In the other direction, we want to associate some ideal to a given set. So for any subset X in projective N space, the vanishing ideal, which again we denote by I of X or IP of X if we need to make precise that this is in the projective setting, this is the ideal generated by all the homogeneous polynomials vanishing at every point in X. We have to require homogeneous in order for this to be well defined. But in particular, this implies that this I of X is a graded ideal. Now, if you take as your ideal the zero ideal, then the vanishing set of this ideal is the whole of projective space. When you take the other extreme, namely you want the vanishing set to be empty, in the affine setting, the only way to do this was to take as your ideal the whole polynomial ring. But here, in fact, it is enough to require that your ideal's radical contains the ideal I0, the ideal generated by all the indeterminates. This is because for this set to vanish, in affine space, the only place where this vanishes is the origin. And this is something you exclude when you construct projective space. So it turns out that the vanishing set of an ideal is empty if and only if the radical of your ideal contains this ideal. As another example, singleton sets are algebraic, so I leave it as an exercise for you to construct for any given point in Pn the ideal whose vanishing set or zero locus this point is. As in the affine case, we want to construct a topology. So as in the affine case with similar techniques, you can prove the following statements. First of all, if two ideals are included in each other, then their zero loci are included in the other direction. Second, the vanishing set or zero locus of a product of ideals is the same as the zero locus of their intersection, which is the union of their respective zero loci. While the zero locus of the sum of two ideals is the intersection of these zero loci. And one can generalize two by the way these products work to any finite collection of ideals, and generalize 3 to any arbitrary collection of ideals. In particular, this means that the finite unions and arbitrary intersections of projective algebraic sets are again projective algebraic sets. From the previous slide, we know that the empty set and the whole space are projective algebraic sets. And so the projective algebraic sets are the closed sets of a topology, and we call this the Zariski topology on Pn, in analogy to the Zariski topology on An. In a affine space, to be a set that is non-empty and closed under scalar multiplication. So this means that if you have x in X, then lambda x is in X for all lambda in K. In particular, non-emptiness amounts to the origin always being a point of this cone. So it consists of lines in An plus 1. It's a union of lines. And why is it called a cone? Well, if you look at the three-dimensional real picture, you can expect something like that, and that is a cone. So that's where the name maybe comes from. Now we want to attach a cone to any projective algebraic set in Pn. So looking at this projection pi from An plus 1 without the origin to Pn, we define the affine cone over a projective algebraic set X to be the pre-image of this projective algebraic set under that projection together with the point 0. So this indeed forms a cone. And what this does is simply for any point in projective space, namely for any line in affine space through the origin, you include the whole line in this affine cone. So this is a cone. In the other direction, if you start with a cone, remove its 0 and project it, you get the projectivization of this cone. So this is the set of all points in projective space that come from lines in this cone. In affine space, to be a set that is non-empty and closed under scalar multiplication. So this means that if you have x in X, then lambda x is in X for all lambda in K. In particular, non-emptiness amounts to the origin always being a point of this cone. So it consists of lines in An plus 1. It's a union of lines. And why is it called a cone? Well, if you look at the three-dimensional real picture, you can expect something like that, and that is a cone. So that's where the name maybe comes from. Now we want to attach a cone to any projective algebraic set in Pn. So looking at this projection pi from An plus 1 without the origin to Pn, we define the affine cone over a projective algebraic set X to be the pre-image of this projective algebraic set under that projection together with the point 0. So this indeed forms a cone. And what this does is simply for any point in projective space, namely for any line in affine space through the origin, you include the whole line in this affine cone. So this is a cone. In the other direction, if you start with a cone, remove its 0 and project it, you get the projectivization of this cone. So this is the set of all points in projective space that come from lines in this cone. In both cases, this removal of 0 and taking closure cancels out, so this is in fact equals to VA of J. So we can replace this part by VA of J. But now VA of J is a cone because J is a homogeneous graded ideal. So since when we have a cone, the vanishing ideal of this cone in affine space consists of homogeneous polynomials. It's a homogeneous ideal. This right-hand side is precisely this ideal. So this has to be exactly this, because here now we are in position to prove the projective Nullstellensatz that you have probably expected would come or been dreading, whichever you did. So the projective Nullstellensatz is the projective analog of the Nullstellensatz, of Hilbert's Nullstellensatz for algebraic sets in affine space. So you might want to go back to that one and refresh your memory. But the projective Nullstellensatz says the following things to begin with. So for any projective algebraic set X in Pn, taking first the vanishing ideal and then the 0 locus, you get back the set X itself. And conversely, for any homogeneous ideal in the polynomial ring, if you take the 0 locus and then the vanishing ideal, you get the radical of the ideal, provided that your ideal is not this problematic ideal generated by the indeterminates. So how do we prove this thing? Well, the first statement is proved as in the affine case. To prove the second statement, it's enough to prove that this IP of VP of J is the same as the affine vanishing ideal of the affine 0 locus of J. Because we know that this thing is equal to the radical by the affine Nullstellensatz. So to prove this, let us look at IP of VP of J. So this is the set of all homogeneous polynomials satisfying f of x equals 0 for all x in VP of J. Now, requiring that a homogeneous polynomial vanishes in all of VP of J amounts to requiring that it vanishes in all of VA of J, except possibly for 0, by lifting it up to affine space, so to speak. And because the 0 set of polynomials is algebraic, it's closed, so it's the same as requiring that this vanishes on the closure in a affine space of this thing. But now, this closure of this thing, so by the previous remark, this is either a cone or empty. So this cannot be, the closure of this is not just the origin, because this would violate the fact that the radical of this ideal is this ideal generated by the variables. You might pause and think why this is the case. So since it is not this thing, it is either empty or a cone containing not only 0. Containing some non-zero x. In both cases, this removal of 0 and taking closure cancels out, so this is in fact equals to VA of j. So we can replace this part by VA of j. But now VA of j is a cone because j is a homogeneous graded ideal. So since when we have a cone, the vanishing ideal of this cone in affine space consists of homogeneous polynomials. It's a homogeneous ideal. This right-hand side is precisely this ideal. So this has to be exactly this, because here we know that this vanishing ideal is homogeneous, so it will be generated by the homogeneous polynomials vanishing at this cone. And this proves that IP of VP of j is equal to IA of VA of j, and we may conclude with the affine Nullstellensatz. Putting these statements together, we can, as before, deduce the appropriate bijection. In our case, we have shown that IP and VP are mutually inverse inclusion reversing bijections between the set of all projective algebraic sets in Pn and the set of all homogeneous radical ideals in the polynomial ring that are not equal to this ideal I0 generated by the indeterminates. The details that were left out of this third part I leave as an exercise.